Alright, let's finish talking about vector spaces so that we can move on to some actual representation theory. So I guess I shouldn't say let's stop talking about vector spaces. I mean, let's wrap up sort of our review of some of the preliminary material. So anyways, okay, so we talked about tensor products, and it turns out just like we could take direct sums of maps, you can do the same thing with tensor products. So if you have two homomorphisms, i.e. linear maps, then you can define the product by starting with this map. So we go from this, just the direct product into the tensor product. And so you map this ordered pair to this vector. And you can check that's bilinear. I'm not going to go through all the details because, again, this is supposed to be more of a review, so I don't want to spend too much time going through all of the little details in all of these proofs, even though I will do it a little bit later on. But anyways, so once you know that it's bilinear, then by the definition of the tensor product, you have an extension of this map. And the extension that you obtain is what you define to be F1 tensor F2. Okay, so that's that. And next, we know that there is a natural injective homomorphism from this tensor product into linear maps from V to W. And so it satisfies this. So if you take this tensor product here, then, okay, so psi or xi, I'm going to call it xi. Xi is in V star, so you plug in an element of V to it, and then you just multiply, and so xi of V is going to give you some complex number, and you're just multiplying that by W. So I guess I should say here for all V and capital V, but whatever. And also where this V is coming from, that's because phi is going to map into the space of homomorphisms from V to W. So in order to specify that map, we're sort of defining it by what it does to an element of here. So yeah, this is sort of the variable. So for any xi and W, phi gives you a map where V is the variable. Okay, so there's a lot going on here, but just try to keep everything straight in your head. So anyways, we start by defining a map like so, and this is basically the map that is going to do what we want it to do, and then we got to extend it. If we want to extend it, we need to check that's bilinear. And I've actually gone through the details here. So fixing the second coordinate for linearity in the first coordinate, this is just by definition of psi. Yeah, so this is psi. So you define psi to be this map that does what you want, and then you extend it to phi or phi, whatever. These Greek letters are sort of weird. So linearity, yeah, okay, so this is by definition. Then going from here to here is because this is an element of V star, and V star is linear functionals from V into C. And so linearity allows you to go from here to here, and then you just use the definition of psi again to go to here, and this to here, this is linearity. As for linearity in the second coordinate, if we fix the first one, this is just by definition, but now this is just a complex number, and this is a vector in W. And so by linearity of vectors in W, you can just distribute this constant through to the two terms. This is basically just multiplication. Distributivity of multiplication. And then there you go, you just replace it with size and you're good. So again, there's no real tricks in these, and that's why a lot of these computations I've left out. Okay, so we now know that psi extends to a linear map phi, which instead of starting from just the direct product, starts from the tensor product. Okay, so that's part of what we wanted. And then we also want injectivity. And so suppose we have some alpha in here. We want to write it as a sum of psi I with wi, where the wi's are linearly independent. Turns out we don't really care about the xi i's in this proof. But whatever. It's just some linear combination of these guys. Okay, so then phi alpha is 0 if and only if this sum is 0 for all v. So for this to be the 0 map, it needs to send, for every v and v, plugging in v is going to need to give you 0. So since the wi's are linearly independent, this means well, maybe it's not because the wi's are linearly independent, but in order for this sum to be 0 for every v and v, you need it to be 0 for every particular I, because if it's not 0 for any particular I, what you could do is you could let v be the vector which is just 1 at that particular coordinate corresponding with that I. Or something along those lines, and then that would work. Okay, so you have this, and then this holds. Okay, so if psi I v of wi is 0 for every single I and v, then for every single I and v, either wi needs to be 0 or xi I of v needs to be 0. So if wi is 0, then you get xi I tensor wi is 0. If so if it's not the case that wi is 0, then xi I of v needs to be 0, and that needs to hold for every single v. And the only way to guarantee that that holds for every single v is if xi I is 0, and then again we get xi I tensor wi is 0. Okay, so then alpha is a sum of the 0 vector a whole bunch of times, and so alpha is 0 in this case. Therefore, phi alpha is 0 if and only if alpha is 0. And so that confirms that's injective, because to be injective means that your kernel is trivial. And there we go. Also, for finite dimensionality, we have an isomorphism. So if V is finite dimensional, that's what FD means. Let's choose a basis for V. And so, of course, because we're using a basis here, we're really using that this is finite dimensional. Okay, so we have a basis, and suppose we have any f in Hom C from V to W. What we're trying to prove is surjectivity, so we're choosing any element in here, and now we want to exhibit an element in here which will map under phi into here. Okay, so we're given this f, and then set wk to be f of vk for all k ranging from 1 to m. Then what happens when we evaluate phi at this sum? Well, if you evaluate f at vi, then what happens if we evaluate this at vi? Remember, the vi is being plugged in here. And we know how we define the vi stars. It's going to be delta ij. So vi star of vj is delta ij. So if you plug in vi into here, then this term, each of these terms is going to be 0 except for the ith term, in which case this part will give you a 1 and you'll be left over with wi. But wi is f of vi. So if you plug in vi here, you're going to get f of vi. And this holds for every single I. And so therefore, these two functions give you the exact same thing on all basis vectors vi. But if it holds for all basis vectors vi, then by linearity, it's going to hold for any vector you plug in here. And so therefore, these two maps are exactly the same. And so this is an element in the domain which will map under phi to this function f, and since that holds for every single f, we have surjectivity. Okay, and now we end this lecture with some sort of really abstract definitions I don't quite fully understand. And again, this is stuff where like I have a reference for a textbook to read for more information about this stuff, but it's at a late enough chapter in the textbook that I don't really understand what's going on, and I don't quite get the words that they're using. But anyways, so you can take v to the tensor k, means you just take v and tensor it with itself k times. And then you can define sim kv, the symmetric product. So what this is you take this v tensor product with itself k times, but then you mod out by taking the span of all collections of vectors that look like this. You take this basis and you take v1 through, oh, is that a basis? It's got to be a basis. No, it's no. This is v, since this is v tensored with itself k times, each vi is just an element from the corresponding v's here. So it's not, there's nothing special about these vi's necessarily. This k is just needs to be equal to this k because they match up dimensionality wise or something like that. But anyway, so we take this tensor product and we subtract itself, but here I minus 1, did I write this down right? Here, these two are flipped. We took vi and we took vi plus 1 and we flipped them. And this is going to hold for every single I between 1 and k minus 1. So basically you can take any two adjacent vi's and flip them. And take this difference and just consider the span of these things. And of course, we call it the symmetric product because this sort of makes you think of the symmetric group in some sense, because the symmetric group is generated by simple transpositions, and yeah, here we're sort of flipping things there. So there's something going on there, but I guess I don't quite understand it well enough to give a really deep insight into why it's called the symmetric product. But you can do the same thing, but I actually didn't write down the symbol for this next part. The alternating or exterior product is written using a capital lambda. So it's lambda to the k of v. And what it is you do the same thing, but in the span down here, instead of having minus, you have a plus. And so yeah, those are two vector spaces that I don't know how much they're going to come up in this course. It might just be like sort of like an aside topic that is used in a handful of places, but not like throughout the course. But anyways, yeah, here we go. This is pretty much our review of vector spaces. We might do a little bit more review, not too much more if we do any more. But after that, we're going to move on and go into representation theory. So that'll be fun.